Actually, first let's discuss the stability of various resonance forms and how we would estimate which form is more stable. Here's an example of a molecule that has two different resonance forms. Which of these is more stable and which contributes more to the overall hybrid? Well, what we'll find is that the greater number of covalent bonds, the greater the stability, because more atoms will have complete octets. So the number one thing we're always going to be looking for to evaluate a Lewis structure is the more we have for complete octets, the better the Lewis structure. That's always our first thing we want to take a look at. So when we compare these two structures, we see that this carbon is missing an octet, while in the second structure, every atom has a complete octet, a total of 8 electrons around it. So this is the more important. This is more stable. We also say, we describe it as being a better contributor. So what does the actual hybrid look like? The actual hybrid looks more like this structure on the right because it is the more stable structure, it is the better contributor. It's more important. It's more important than the first. Important. Because this is missing an octet, this is less important. Okay, and finally let's see if we can use curved arrows to get some practice shifting electrons around. How would you say what's changed in going from this structure on the left to the structure on the right? Looks like this lone pair of electrons that used to be on oxygen is now being shared between the oxygen and the carbon as a pi bond. So what we do is we use an arrow, a curved arrow showing these two electrons picking up and moving to be between the oxygen and the carbon. So this is a really good habit to get into so we can keep track of our electrons. Really important for bookkeeping for electrons when we do curved arrows. Okay, another thing to look for is if we have a separation of charge, if we can avoid formal charges, that would be a very good Lewis structure. So that's something to keep in mind. So if we compare this first structure to this next structure, those are both valid Lewis structures, but this is going to be the most important because this one has formal charges. And how about comparing this second one to the third one? Which of those is more important? They both have formal charges. And you might think about bringing that plus and minus closer together. That would be a good thing, except something else is missing in this last structure that makes it not as good as the middle structure. Looks like we have, with this carbon again, a carbon with just 3 bonds. This is missing an octet. So this is the least important because octets are the most significant thing that we're going to be looking for. And again, covalent bonds are something you can look for. I lost a covalent bond in this structure, so that tips me off to the fact that I must have lost an octet. Let's do some curved arrow practice and going from this first to second structure. How do we convert that? This lone pair moved in to be a pi bond, and then this pi bond moved up to be a lone pair. Notice our formal charges have been created as a result. You can practice with those, double check those charges are right. And how about going from this second structure to the third structure? We've taken this pi bond and picked it up and moved it to be a lone pair on nitrogen. So we're moving pi bonds and we're moving lone pairs to do this resonance. Okay? Our third rule is that all other things being equal, a structure with a negative charge on the more electronegative element will be more stable. And similarly, if we have a positive charge that we're delocalizing, positive charges on the least electronegative atom will be more stable. So for example, when we look at this carbonyl, a CO double bond is called a carbonyl, we can pick this lone pair up and move it to the oxygen to give a C plus and an O minus. Or we could pick this lone pair, this pi bond up and move it to the carbon to give a C minus and an O plus. Now one of these resonance delocalizations is quite significant and the other is very unlikely. And because oxygen is more electronegative than carbon, the oxygen prefers to have the negative charge, better handles the negative charge. So this is important resonance. And this resonance is unlikely. And then finally, resonance forms that are equivalent have no difference in stability and contribute equally. So sometimes we might compare two resonance forms and not find any significant difference in their structure. For example, this guy is known as the allyl carbocation, and they both have one double bond and one carbon missing an octet, double bond, carbon missing an octet, and so because they have equal features of stability, they're going to be equal in energy and therefore contribute equally to the resonance hybrid. Okay, let's show our curved arrows. Looks like this pi bond is picked up and just jumped over to be on the other side, and as a result this positive charge will now be on the N carbon. Notice that with my arrows I'm never moving the charges. Our curved arrows only move electrons, so they're either going to start at a lone pair or they're going to start at a pi bond, and the charges will move as a result. So we'll just calculate those charges on the new Lewis structure.